All right. So this shape is what we refer to as an irregular shape. Okay. Meaning that we don't have like a specific formula for it. Does that make sense? All right. Sometimes they're referred to as composite shapes. Composite meaning that it's made up of many smaller things. Does that make sense, everybody? My hope is that you can see here that we have a triangle and a square, correct? Okay, so we're trying to figure out the area of this thing. So the way I like to do this is I will break it down into the 2 or 3 or 4, just depends on how many there are, composite, smaller composite, or smaller components, I guess should be the word I'm using, that make this overall composite shape. So there is a triangle, so we'll find the area of the triangle. Okay? So the area of the triangle is always 1/2 BH. So I need to establish what is B and what is H. Okay? Okay, so which one is H? Okay, so in the way that we define this, that is the altitude, and that becomes H. Okay? The reason I asked, which one is which is because, and the multiplication in the formula doesn't matter because multiplication is commutative. But the reason I would want to know that is because if I define that as H, then it automatically defines what I have to use as the base, and I have to use that as the base because that is the segment that the altitude is drawn to. Does that make sense? Okay, so that distance there then would be 6. Okay, so we get 6 times 8, 48. Half that's 24, right? Okay, then we'll look at the area of the square, which is s squared, which would be 36 in this case, 6 times 6, right? Now, what am I going to do for the composite? The area of the total would be 24 plus 36 equals 60 inches squared. Okay, now here's my question to you. Let's put that in feet squared. I think at this, we're going to go through about 3 or 4 examples here, and I think we're going to have time to learn some additional mathematics that is going to be part of the rest of the course that I think right now would be a good time to talk about. It's called unit analysis, or dimensional analysis. Okay, dimensional because these are dimensions. So we call it a two-dimensional shape, but a length and a width, or a base and a height, are dimensions of this 2D figure. Okay, I want to be able to change this into feet squared. So here's the thing, and this is the number one answer that I get wrong, or that people give me that is wrong, is that they say that they need to multiply that by 12 or divide that by 12, one of those two. Okay, and that is incorrect. Okay, and the reason for that I want to show you is if I want to change this area into feet squared, that would be equivalent. Let's just talk about the area of the square. I think it would be easiest to talk about that one. If I want to turn that, and that's 36 inches squared, if I want to turn that into feet squared, prior to doing any of the work, what would I have to change that 6 inches to? 1/2. And that changes to 0.5 feet, correct? So I took 6 and divided it by 12, correct? Make sense? What do I have to turn that side length there into? If that's 6 inches as well, then I have to change that to 0.5 feet. What did I divide that 6 inches by to get 0.5 feet? I divided by 12, right? How many times did you divide by 12? You divided by 12 twice. Okay? So I divide by 12 twice, I've effectively divided by 144. Does that make sense? Okay? So the number, like I said, the number one answer I get that is wrong is that people want to divide by 12. That you can actually do that twice. Okay, you're going to divide by 144. Now, what I'm going to show you is actually an approach that is going to be hopefully one that you've already learned in science, but you probably only learned it in singular dimensions. Okay, I'm going to use conversion factors to get this thing into feet squared. So what I always do, start with what you currently have your answer in. It's in terms of inches squared. And I want to get it into feet squared. So I give myself a good amount of room because I'm going to fill some values in here. But I put the units that I want in my answer at the end. And that just gives me a visual to remind myself of where I'm at and where I need to go. Okay? If I want inches squared to go away, what I need to be able to do, because inches squared or any unit, we treat it the same as a number, okay? So if inches are in the numerators and I want inches to go away, I need inches in the denominator because they'll cancel that way. Does that make sense? Inch over inch cancels to 1. Like 60 over 60 would cancel to 1. Does that make sense to everybody? Okay. So if right now I've got inches squared up here, which just to prove a point is inches times inches. Okay, that's still inches squared, right? If I want those to cancel, then I'm going to need an inch right here. And that red one there and that black one there will cancel. Does that make sense? Now, here's my question to you. And this is what you're always going to ask yourself every single step. Is there a direct link between inches and feet that you want to go to that is a common knowledge value? Is it easy for us to go between, do you know how many inches are in a foot? That's basically what I'm asking. You do, okay? Now, if I were to ask you, do you know how many inches are in a mile? You probably don't know that, right? That's not a common knowledge value. So we would have an intermediate step that would get us eventually to miles. But there's a direct link here between inches and feet. So that's good, okay? If I left it right there, and this is what normally people do, 1 foot for every 12 inches. We go and plug those values in. Normally what people do when they're wrong is they divide, I said they divide once by 12, right? If they did that, their answer is actually in inch feet. That would be your unit, in inch feet. And that makes no sense at all. Does that make sense? Okay. So I still have an inch here that is in the numerator. So I need another inch in the denominator. That inch will cancel with that inch. Is there a link between inches and the unit I want to go to? We've already established that. I go 1 in 12. Okay. I think that's the best thing to do is to always, whatever your larger dimension is, feet is a larger dimension than inch, right? So always let your larger thing be a value of 1. And then you have 12 inches that make that one thing, right? I could make inches 1 and then figure out, okay, well, if inches are 1, how does that relate to feet? But that's just a messy thing to do. Now, if I look at the units, what are the only units that are left over? Feet times feet, and that'll give me the feet squared that I want, right? If I multiply straight across, so this is a fraction over here, 60 over 1. Straight across the top gives me 60. Straight across the bottom gives me 144. So then I need to take 60 and divide it by 144. And we get 0.416 repeating. 0.416 square feet. Kind of make sense on how to do that? All right. The reason I talk about that's not a big geometric concept. It is a huge science concept. Okay. You guys dealt with Avogadro's number in science, mole road, and all that kind of stuff. It's disgusting. Somebody put gum on a piece of paper and folded it and left it on the desk. You guys have dealt with that, like changing like molar mass into all the stuff that you changed into. Would you agree that was a confusing thing to do? If you understand how units cancel, you will have such greater success in that science area, okay? A lot of the courses that I teach beyond geometry, we get a lot of story problems, and if we're not certain on how to do the process in the story, but we understand the units that they're providing us and the units that we want to get to, it might elicit how to manipulate the formula or manipulate the objects that are in the problem to get where we want to go. Does that make sense? So an understanding of dimensional analysis or unit analysis, I think, is very, very important. You've done it a lot in science. What's the number one system that you guys use in science for dimensions? Huh? The metric system. I don't know why all my work is disappearing here, but so you guys know that King Henry died by drinking chocolate milk, right? Now that's only a snapshot of the metric system. You can go, you guys have heard of, so we got kilo, you've heard of mega, you've heard of giga, you've heard of tetra, right? Gigabytes, you probably heard them with in regards to computer terminology, gigabytes, terabytes, megabytes, that kind of thing. So those are things that we go this way. We can also go this way with, so we got milli, we can go micro, we can go nano, we can go pico. So there are greater ends of the spectrum of the metric system. But this has been your base, and this would have been, if we're talking about distances, you would have been in meters. If we've been talking about masses, you're in grams. And if we're talking about volumes, you would have been in liters, right? Okay, but we can go from liters to deciliters to centiliters to milliliters or whatever, okay? So let's say that I give you something that says, let's convert let's go this way. Let's go, I want to say we have let's go 20,481 centiliters. Okay. And I want to convert that into kiloliters. I want to get all the way to KL. You guys know from King Henry died by drinking chocolate milk, if I'm at centiliters, I'm right there, correct? And I'm going to go 1 spot, 2 spots, 3 spots, 4 spots, 5 spots, right? Which means that my decimal point right there needs to follow the same progression. 1 spot, 2 spot, 3 spots, 4 spots, 5 spots. It should give me that. So 0.20481 kiloliters, right? So you've used that device. However, when you're using that device, what you are doing is the following. If I start with 22,481 centiliters, okay, and I want to go to kiloliters, okay, I'm going to do this in a couple different steps, okay? Centi, what's the prefix centi mean? Where do you see cent the most? So it means 100, okay? So we have 100 cents in a dollar, right? We have 100 centimeters in a meter. So that means we have 100 centiliters in a liter. Does that make sense? So if I put CL down here and L right there, those should cancel out, but I should be able to say that I have for every 1 liter, 100 centiliters. Okay? I could have done that a little bit more deliberate. I could have said there are for every 1 deciliter, there are 10 centiliters. And then for every 1 liter, there are 10 deciliters, okay? Because these are powers of 10 as we go through here. But I think centi is a prefix that a lot of people should know. It's common knowledge. Then I'm gonna multiply that. So right now, if I multiply this all out, I would be left with an answer in liters. I don't want an answer left in liters. I want an answer in kiloliters. Okay. How many liters? So liters is gonna be down here because I want those to cancel. How many liters are there in a kiloliter? Kilo. That prefix refers to what? What does kilo refer to in science people? If I have a kilogram, how many grams is that? Think about this. If I go, so let's say that I have one kilogram, 1.0 right here. And I want to go to grams or liters, whatever base I want. How many spots do I need to move into a decimal? 1, 2, 3, right? So 1,000. So kilo, that prefix means 1,000. So if I look at this, so I would multiply, so 1,000 liters for every 1 kiloliter. Okay? Well, when I do this, this turns in, so I multiply this all out. Okay, so everything cancels, I'd be left in the units that I want. I'd have 20481 divided by, it's going to be 1 followed by 5 zeros, right? Okay, if I do that division, the number of zeros, when I do division, tells me how many places to move my decimal, right? Moving it to the left 5 spots, which is what we knew when we did King Henry died by drinking chocolate milk. Moved it along that slider, right? So when every time you use this, you are really doing this, but you're circumventing all the work. Does that make sense? Okay. This is a power of 10 tool. This is why the metric system is so useful, is because this is 10 to the 0 power. Your base, 10 to the 0, is always 1, right? So that's why it's my base. It's my unit that I start with. This is 10 to the negative 1. This is 10 to the negative 2. This is 10 to the negative 3. 10 to the negative 2, just to use the one that we used here. 10 to the negative 2, negative exponents from algebra turned into that, didn't they? And if I have 1 over 10 squared, isn't 10 squared 100? So we were at centiliters. We want to go to liters. There's our conversion factor. Okay? This is 10 to the first. That's this is deci over here, D-E-C-I, and this is deca. But that's 10 to the first. This is 10 squared, and this is 10 to the third. Okay? Mega goes 10 to the sixth. So after you get through, usually if you go to like Wikipedia or something and look at metric system. There should be a list here somewhere of, there we go. You see our 10 to the third was kilo. Okay, then we go 10 to the sixth, so there's quite a bit of jump there, right? Okay. So there's 1,000 kilobytes in a megabyte, or there's 1,000 kilograms in a megagram. Okay. That's 10 to the sixth, and then there's a billion, which is a giga, and then there's a trillion. Okay, and I can keep going, and then it goes in the opposite direction with micro, nano, and pico as well. But that kind of makes sense. Obviously, you guys have learned King Henry died by drinking chocolate milk because those in just a traditional science chemistry class, you're not working with things kind of on the very, very, very minute scale. Okay, usually like if you're in quantum mechanics or something like that, you're talking about these values. Because at that stage, you're talking about atoms and protons and neutrons and those things. Is that cool? Can we do that stuff? I'm going to ask you because I think that's a byproduct of geometry. I don't think seeing that this is maybe a rectangle and a triangle, and I'm going to add their areas together, but that is a complex situation. Okay, I think we should all be able to master that within a day or two. So we've got room to be able to build on to that and maybe have a byproduct that we benefit from. This one's a little bit, this is still a composite function or composite object shape, okay? There's still a triangle, and I don't know if that's a square, and that's the thing that we want to make sure we realize here, because a lot of times people say, oh, that bottom shape, because of the one we just did, is always a square. Even if it looks like a square, it might look like a square, okay? But we don't know that, okay? Now, if I'm looking at that triangle on top, and I want to find its area. Area is 1/2 BH, right? Okay? You have options here. I think some of those options are going to be easier than others, okay? My suggestion to you is decide what you want your base to be. If I'm looking at that triangle, what number, 25 or 7, makes more sense to find out what my base is? Would you rather just tell me one. Do you want to use 25 or 7? Okay, 7. I think 7 is appropriate. If I were to use 25 as my base, that would mean that I have to find out that length right there to be my altitude. Does that make sense? Do you see how finding that red distance would be hard? Okay? But because it's a right triangle, if I let 7 be my base, then this dotted line is going to be my H, or my altitude. And that might be, even though it's unknown right now, that might be easier. Okay? How can I find that distance right there? Pythagorean theorem. It's a right triangle. You know 2 of the sides. We should be able to say H squared plus 49, which would be 7 squared, should equal 25 squared, which is 625. If I take 625 and subtract 50 from it, what would that give me? If I had $6.25 and I removed 50 cents from that, it'd be $5.75, right? But I actually subtracted 1 more than I wanted, so I'm looking at $5.76. If I square root that, you might know what the square root of 576 is. Jagger, do you know the square root of 5? Jumpy. Do you know what the square root of 576 is? So no. Huh? $24. Okay, so now we got H, we got B. Okay, so when I plug those in, we're going to have 1/2 7 times 24. When I have it written that way, 1/2 times 7 times 24, do I distribute it to 1/2? Is that what I'm saying there? When I write that way? So I take 1/2 times 7 and then 1/2 times 24? No. Okay? So, order of operation says add, subtract, multiply, divide, left to right as you see them. So you're going to multiply those two, get a result, and then multiply those two, right? So you do not distribute the 1/2 everything. Now, I wouldn't do it that way because 1/2 and 7 don't work well together, right? The 7 is odd. But the commutative property tells me I can take those two and multiply them together. What's that give me? 12. What's 12 times 7 then? Carry your 1. Be 84, right? Okay. And now my rectangle, it's good that we called it a rectangle because now we know that's 24, correct? Okay. So rectangle, base times height, is going to be 21 times 24. I'm going to do it this way. I'm going to write it as 20 times 24 plus 1 times 24. If you guys remember back to, your parents hated the new math that the Common Core was coming out with, right? Because they forced you to take 21 times 24, which we want to do in our head, which your parents learned by memorization, to break that down as the 20 times 24 plus 1 times 24. Because that is easy to do in your head. What's 2 times 24? 48, right? So this is 480. And what do I get if I take 480 and add 24 to it? 504, right? So now what am I going to get when I add these two things together? That one and that one. 588. And what's my unit? Feet squared. Let's put give me another dimension. Give me a different. Let's do this. Let's see how many millimeters that is. Millimeters. So what we're going to do is we're going to take this 588 and see how many millimeters squared that is. Now, here's my question to you. Initially, why is that a problem? Why is this going to be hard to do? Okay, so feet is the U.S. customary. Okay, it's in that system. Millimeters is in the metric system. Okay, we got to be able to cross over. Okay, we can do that. So here's what I think we should do. Let's get this into inches. So if I want to get it into inches, feet need to cancel, right? So I'll put feet there, and I'll need another multiplication. So those two feet down there are going to cancel with all the feet up there, right? So now if I multiply through, I'd be in inches squared. Okay? Now here's where we make the transition into the metric system. Okay? 1 inch equals 2.54 centimeters. That is a common fact, much like saying 1 foot equals 12 inches. Okay? But this is a fact that allows you to go from one system to the next. Okay? If we were to put a meter is, I think we've talked about this, the meter is described, it's defined off of how fast the distance that a light particle travels in a vacuum in a fraction of a second. Okay? I forget what the fraction of a second is. It's a very, very small amount of time. But because we know that, we can say, okay, well, how long does that take that light photon to move an inch, and compare it to how long it takes it to move along that meter, and we can get this. Does that make sense? Okay. So I'm going to take this and say, okay, if I put inches there, that inch and that inch will cancel, but I got a conversion now to get me to centimeters. Put another inch here. It will cancel with that one, and I get the centimeters. So now, if I multiplied everything out, my answer would be in centimeters squared. Not what I want. Well, millimeters squared. And King Henry might help you here if you don't know this. But if this is centi and this is milli, that's a difference of 1 power of 10, right? So there's 10 millimeters for every 1 centimeter, right? So there's a direct link there. So I can go centimeters here, millimeters there. Those will cancel. and millimeters here, and centimeters there. And those will cancel. Okay? Now, I haven't put any numbers in, and I never put numbers in at the onset. Because if my units are wrong, it doesn't matter what the numbers are, right? I have to make sure that my units match up first. Okay? So as I go through, everything canceled out except for millimeters and millimeters, so I should get millimeters squared. Now I'll go back in, put my numbers. Inches and feet. What number should I put here with inches? 12 inches for 1 foot, right? 12 inches, 1 foot. Centimeters to inches. That right there. 2.54 centimeters for 1 inch. 2.54 centimeters to 1 inch. Okay? We said there was a rate that there are 10 millimeters for every 1 centimeter. So in this case, if I want to go from feet squared to millimeters squared, it turns into all multiplication for us. So we go 588 times 12 times 12 is 144 times 2.54 times 2.54, then times 100, and that would be how many millimeters squared that is. So that's, what, 54 million square millimeters. Is that all right? Anybody know what that shape is? It's a kite. Okay? Now, as we progress through the course, through this chapter, we'll actually get another formula for this. But right now, it's a shape that I don't know how to find the area for, because we have two areas, 1/2 BH and BH. So, is this broken up into triangles? Okay? So we'll call this triangle 1 right here. Okay? Now, we talked in chapter 6 about the diagonals of a kite. What do the diagonals of a kite do to one another? Okay, one of them gets bisected. Okay, if I look at that horizontal one does not look the same on both sides of where it's getting cut, right? One side is 2 meters and the other side is 5 meters, right? But the vertical diagonal is getting bisected, right? So that's true. One diagonal bisects the other. What's another property? Nope. Okay, they can't be. If they don't bisect each other, they can't be equal, because then one is 7 meters long and one is 8 meters long. Okay, they're perpendicular. Diagonals of a kite are perpendicular. So, when I find the area of triangle number 1, area is 1/2 BH. What do you want your B or H to be in this case? We want B to be. If B is 5, then what's the H? 4, right? And remember what the H was? It's the altitude. Do you guys remember in right triangles that the legs of your right triangle are altitudes? So in this case, we chose 4 to be our altitude. But is there anything wrong with letting 5 be our altitude? And then 4 would be the base. But regardless of that choice, 5 times 4 or 4 times 5 always gives you 20, right? So in a right triangle, the leg, if you have both legs, one of them is the base, one of them is the altitude, and it doesn't really matter which is which. So I'm going to multiply those. So obviously that gives me 10, right? What do I know about triangle 1 and triangle 2? They're congruent, right? So can I multiply this area by 2? Multiply that area by 2. And so far, everything that is blue here would be 20 square meters. Okay. Now we got to work on the triangles on the left. So I'll call this triangle 3 here. So area of triangle 3, again 1/2 BH. What kind of triangles would those be? Still right triangles. What do you want B to be in that case? B to be 2? Then you're going to choose H to be 4, right? So that would be 4. But this triangle here and this triangle here are the same, so let's just double that, and I get 8. So what we're going to do with that number and that number? Add them together. 28 square meters. Is that all right? Okay. What is this shape down here? Because these are both right angles, what's that tell you about this top line and this bottom line? They're parallel. Okay. These are same side interior angles, and same side interior angles are supplementary. Then the lines that are cut by the transversal are parallel. You have one set of parallel lines. What's the definition, or what's the vocabulary word for the definition of a quadrilateral with one set of parallel lines? Starts with a T. That's a trapezoid. Okay. Usually, that's we call that a right trapezoid. Usually, you guys are accustomed to like your trapezoid looking like that, right? Okay, but it doesn't have to. So my hopes are you can see that we will eventually have a formula for this as well, but right now we don't have that formula. So how can I address this? Okay, and a lot of times what you're going to see is that they won't give you this dotted line, which that dotted line is your altitude, right? That makes sense? It goes from one side perpendicular to the other side. It goes from one of the parallel sides perpendicular to the other side. Okay, they won't always give that to you. They won't draw it in. But that's the best place to put it, okay? Because when I put it there, it takes our irregular shape and makes it into a composite of a triangle and a composite of a rectangle, right? Now, I don't have the dimensions for finding the area of the triangle or finding the area of the rectangle. This is where still doing stuff that we talked about in 8th grade, 7th grade, maybe with areas. But in 7th grade, they gave you that number. Here, we got to determine them. What do you notice about this triangle right here? 30, 60, 90. So if it's 30, 60, 90, the hypotenuse is always 2 times n, right? 30, 60, 90. So what would n be if I had that equation? 2. And that was always across from 30. So it's that distance right there. Okay. This side across from 60 is always n radical 3. Okay? It's a right triangle. So if I want to find the area of it, it's 1/2 BH. What do you want your base to be? In the triangle? 2 radical 3. Am I wrong when I ask that because it's a right triangle? Am I ever wrong with an answer? No. 2 radical 3 is the base because it's an altitude. Okay? So if I want that to be the altitude, then 2 is the base. But if I want 2 to be the altitude, then 2 radical 3 is the base. Doesn't matter, though. So we should be able to multiply that stuff out and get 2 radical 3 square feet for the green triangle. What's the area of the rectangle? 16 square feet, right? How do I write the area of the trapezoid? What do we do with those two things? You add them. So 16 plus 2 radical 3 square feet. I cannot converge them. I cannot merge them into one number because 1 is rational, 16 is rational, 2 radical 3 is irrational. We don't like to merge those. Okay. Now, if they ask you in Math Excel to type in the 1 decimal place, 2 decimal places, that kind of thing, type that in your calculator and you can go out to whatever decimal you need. But that would be the exact area of that shape. Okay. So hopefully that's a demonstration of showing you as you do your homework, they're not going to give you all the components that you need for your formulas. They will give you all the necessary information that will lead you to determine those components, but they're not going to explicitly just hand them to you. You might have to dig for them a little bit. Do you have questions on this? All right, we'll continue that theme about conversion, unit analysis. That's going to be consistent for the next 9 weeks. Okay, that'll be a procedure that we continually build on and get stronger at. I think it will help you mightily in your science classes. Okay, there's an assignment 10.1 available. You can work on that for the remaining time. Work together if you want.